Okay, class, in this lesson, you are going to learn to write exponential models in different ways to solve problems. So part of these problems will be a review from prior math classes, but this is sort of a consolidation of exponential problems. So let's go ahead and get started. Here's the first equation for solving x. Normally, we would use natural logs to solve this, but in this particular example, I'm going to show you how to solve this by graphing. Okay, so we have the following problem: 5 to the 2x power plus 36 is equal to 662. The challenge here is that we have x in the exponent, and so you're going to need to use a different technique to solve this. And by graphing, is one way to do this. And so what you're going to do is rewrite this equation as follows. So you're going to subtract 36 from both sides. And when you do, you're left with 5 to the 2x is equal to 626. Okay? And so you're going to graph two different lines. You're going to graph this function, which I've written here as y is equal to 5 to the 2x. And then you're also going to graph y is equal to 626, okay? And that comes from this part of the equation. So basically, we're graphing two functions. So we know that this is going to be a horizontal line, and this is going to be some sort of exponential function. And where both of these graphs intersect is the solution, okay? So you could use any graphing tools. I normally use Desmos to do this. And when you do use Desmos, what you're going to need to do is move up to this area of the y-axis, okay? So this is way, 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 way up on the y-axis, so you're going to need to zoom out quite a bit, scroll up, and then zoom back in. And what you'll notice is that this intersection, if you click on this intersection, this point will actually show up, okay? And it's going to show an x comma y, okay? So remember, these coordinates are going to be x comma y. And our answer is going to be the x value of the coordinate. And you'll notice that the x is stated as 2.0005. So in this particular problem, if the problem states to provide an answer to the nearest hundredth, then your answer is going to be x equals 2.00, okay? 2 places to the right of the decimal is the hundredths place. Okay, so that is how you solve this problem by graphing. So let's move on to the next problem. Now we have another rational equation to solve where we have the x's, again, in the exponent, okay? But I'm going to show you how to do this without using a calculator. If you notice that the base here is a 2, and we have a base of 4, okay? Now using the exponential rule, if we can get both of these bases to be identical, then we can eliminate those and solve for just the exponential values. So to do that, we're going to go ahead and rewrite this equation as 2 squared, okay? 4 is the same thing as 2 squared, and that's raised to the x plus 9 power, okay? So in this first step, we wrote everything exactly the same. The only difference here is this 4. We rewrote this as 2 squared. All right, so now when we have, as part of another exponential rule, if we have a power raised to a power, then that allows us to multiply them together, okay? So then this becomes 2 to the 5x minus 5. Nothing changes there. This becomes 2 to the 2 times x plus 9 power, okay? So again, when you have a power raised to a power, it's the same as multiplying them together. Okay, now what we've accomplished is getting the same base. This is a base of 2, and on this side we have a base of 2, which means we can go ahead and knock those out and just solve for the exponential values. So here we've got 5x, I'm sorry, not plus 5, it's going to be minus 5. 5x minus 5 is equal to 2 times x plus 9, okay? And then solving for x is much easier because now it's just basic algebra. This comes out to 5x minus 5. And then on the right side, if we use the distribution, we get 2x plus 18. And then subtracting 2x from both sides, we get 3x minus 5 is equal to 18. And then if we add 5 to both sides, okay, then we're left with 3x is equal to 23. And then finally, dividing both sides by 3, we isolate x and get x is equal to 23 over 3, okay? And so this becomes the answer to this problem. Okay, let's move on to another problem. Here we have a scenario that's very common, and you will encounter these types of problems somewhat frequently. Emily can build a rocket in 3 hours, and Irvin can build a rocket in 5 hours. How many hours would it take them to build the rocket if they work together? Okay, so we've got two individuals, and you're being told how long it takes them to do a particular task. And then the question here becomes, well, how long would it take if they both work together on the same task? Okay, so the way to set this problem up is Emily can build a rocket in 3 hours, so that is 1 over 3. And we're also going to include what Irvin can do, and he does it in 5 hours, so that becomes 1 over 5, and that is equal to the sum of them, which is going to be what we're solving, so that's going to be 1 over x, okay? So setting this problem up is probably the hardest, and then from here on, you can just go ahead and solve for x. Okay, so obviously, we can't add these two fractions together until we have a common denominator, okay? And we can get a common denominator by multiplying this first fraction by 5 over 5, and then the second fraction by 3 over 3. And by doing that, you'll notice that 3 times 5 becomes 15, and 5 times 3 becomes 15, and that's how we achieve the common denominator, okay? So then this first fraction comes out to 5 over 15, and that's going to be plus 3 over 15, and that's going to equal 1 over x. Now that we have the same denominator, we can go ahead and add these two together. And this becomes 8 over 15, and that is equal to 1 over x, okay? Then what we're going to do is we're going to cross multiply. We're going to cross multiply. I'm going to just note this here. We're going to cross multiply these, meaning 8x is equal to 15 when we cross multiply. And then the last step here is going to divide by 8 on both sides so that we can isolate x, and our answer becomes 15 over 8. All right? So that is how you solve these types of problems. Okay, moving on to example 4. All right, now we're really getting to the exponential models. Here we have a situation where we have a contagious virus that is spreading throughout Los Angeles. It infects 10 people in the first hour and doubles every hour after that. Okay, and the question is, how many people will be infected in 12 hours? All right, so we're going to need to put together an exponential model, and the base of this is going to be f of x is equal to a times, I'm going to just go ahead and give it another letter. I guess I will say here it's going to be 2 to the x power, okay, where a is going to be your initial amount that you're starting with, and this 2 is the doubling effect, okay? So when we're doubling, you're going to have a base of 2 raised to the x power. And so when we go ahead and solve this, we're going to say, well, we're going to need to answer the question, how long is it going to take, or how many people will be infected in a matter of 12 hours. So the way to set this up is this is going to be f of 12 because we're solving for 12 hours. All right. The initial amount was 10 people times, and it's going to be 2 to the 12th power. Okay, 2 to the 12th power. So 2 to the 12th power is, if you punch this in the calculator, comes out to, let's see here, 2 to the 12th power is going to be 4,096, which means that it's going to affect 40,960 people in 12 hours. Okay, so the key thing here is putting together this model where, because this is a doubling effect every hour, we use a base of 2 to the power of x to determine however many hours are being asked. In this case, it's 12. And then we have to remember the initial amount of 10 in the first hour. Okay? All right, so let's go ahead and move on to another example where we're also using an exponential model, but in this case, this is an investment model. So here we're saying that as a high school student, you're working part-time, and from now until the age of 18, you're able to save $7,000. And the question here is, if you invest that money in an account that grows 12% each year, how much would you have when you retire at the age of 65? Okay, so here we're going to start with the following function. I'm going to just call this f of t, okay, is equal to, I'm going to say a, which is my initial amount, times 1 plus r raised to the t power, okay, where a is equal to the initial amount, r is the rate or interest rate, and then t is time or the number of years, okay? Now, one caveat here is that if you notice in this word problem, the question is each year, okay? This is also another way of saying annually. Now, the equation that I provided you only works if we have a model that compounds annually, okay? So in other words, if the problem had changed to semi-annually, quarterly, or monthly, then you can't use this equation, okay? There's a slight variation, but for the purpose of this particular lesson, we're going to just focus on annually, and so this equation will work. All right, so let's go ahead and plug in our numbers, okay? So we're talking about f of t. We want to know what happens, or how much you will have at the age of 65, okay? So the age of 65 mean from the period of 18 years is 65 minus 18 is in 47 years, okay? So what we're solving for essentially is what happens after 47 years. The f of 47 is going to equal, and we're going to start with 7,000, which is our initial amount, times 1 plus the rate, the growth rate is 12%, so we have to express that in decimals, so that's going to be 1 plus 0.12 raised to the 47th power, okay? Now, if we go ahead and enter that into the calculator, you will see that you will have about $1,439,942.35. Okay, so that is how you solve this problem. So you'll notice that this equation is very similar to the one earlier, okay? The only difference here was we have a doubling effect, so we put a 2 in there. This could have been a doubling effect if the account grew by 100%, so that would be a 1 plus 1, okay? But since it's only growing at 12%, we have to take into account this r, okay? All right, and then the last example here is a depreciation. So the previous two problems was all about numbers that were getting bigger and bigger. Here we're going to solve a problem where a number is going to decrease exponentially, okay? And a perfect example to show how this works is with buying a car, okay? So everybody knows that when you buy a car, as soon as you drive it off the lot, the value of that car drops, okay? So here we have a scenario where you're purchasing a car in the amount of $25,000, and it says that the car depreciates at a rate of 15% each year. We want to know what will be the value of that car after 3 years, okay? So our equation is going to be the same. We're going to just call this f of x is equal to a times 1 minus r to the x power, okay? Because this is depreciating, instead of having a 1 plus r, we need to have a 1 minus r, okay? So then this becomes f of 3, because we want to know what the value is in 3 years. That's going to equal 25,000 times 1 minus 15%, which is expressed in decimal. That comes out to 0.15 raised to the third power, okay? Now if you go ahead and punch that into the calculator, that will come out to $15,353.13. So that would be the value of a car depreciating 15% each year after 3 years. Okay? All right. So hopefully that made some sense. If any of this was confusing or if you need clarification, please go back to the beginning of the recording and listen to this again. Thank you.